All right, so it says that we are live.
We are live. All
We
right.
are live. Yes, LRVS 2024. Great, perfect. We're here for this year. Definitely here for this year. And I'm seeing everybody now joining in. I know Ahmed was here from the get-go before time, always early. Good. William Sloan is here as well. We have Greg Livingstone. I know it's early for Greg on his side, so we appreciate you joining us so much and taking the time out to get here. Hi, Ahmed. We're glad that you are here with us. We have everybody now joining in and just coming in, getting your coffee or maybe another drink because it's a different time zone for you. Because we have a lot of different time zones going on today. Martins is joining in. Jed is joining in as well. Like we have lots of LRVSs across the world, so I know you all will be ready for this. And it is LRVS 2024. It's so this year we're a little bit different. We're trying to make sure that we can reach you all in every possible way. So we figured, why not try a LinkedIn Live? And why not try a YouTube Live? And why not try a StreamYard? Because everybody should be able to access those different things. And it's all about being able to bring the content to you all because we have so many experts in this field and they're just ready to share their content. I mean, we have a great lineup of speakers today. I know, like, definitely great lineup. We have Andre coming in from Canada. We have Hassan coming in from Egypt. We have Mike Johnson coming in from the US. And then, of course, we have Blair joining in from Canada again. Canada seems very popular this morning. And then we have our panel session with Robert Torres, Jim Hannon, and of course, Greg Livingstone. So it's going to be like a very fun, packed 3 hour session that we're going to be running from now until 12 noon Eastern time. Because I know we have Martins coming in from Nigeria. I appreciate you joining so much because the different time zones, it's like, wow. Yeah, definitely love the fact that you all can join.
This is a global community.
It
I love it.
is.
And yeah,
Well,
said it nicely, right? So many familiar names, and it feels like
yes.
family now. And that's the intent. Yeah.
That's always been the intent because LRVS is a community where we can all come together. We have Saudi Arabia here. I love to hear Saudi Arabia being in the mix as well. So it is a community, and one of the great things about LRVS is that we're always able to meet together and help each other out. And I have a fantastic story about our first set of presenters for the day, and I will get to that when I'm ready to bring them on stage. But that is what LRVS is about, and that's what it stands for in terms of everybody coming together just to share information, to share knowledge. We leave all of the other things on the outside, and this is our safe space to have this community where we can speak freely and share information because that's what it's about. It's really about just sharing the information.
There's so much learning to be had, and
Oh yes,
yeah.
get your notepad ready. I have mine.
A couple minutes, right? So this is going to be recorded. So if you have to top up your coffee and you miss a session,
Yes,
you could always come back and see the
definitely.
materials. Yeah.
Yeah. So I'm gonna get Hassan and Andre ready because I know you all are excited about them joining this morning. So one of the great things with Hassan and Andre is that they actually met during LRVS and they had a beautiful project that they were starting to work on. And they were like, we need to pitch this to LRVS 2024 because of LRVS that they were able to go on this project. And they wanted to share some more information on that. So I'm going to bring them on stage right now because, they are ready. Of course, they're ready. And what they're going to be talking to us this
Yeah.
morning about, oh boy, yes, you all are. So We have Andre with us and we have Hassan with us, and they're going to be taking us through building a PF curve. Now, PF curves and I have a very strange relationship, but I'm going to leave that right there. Um, this is actually to get, it's an example that they're going to be doing within the industry and something that they worked on because after LRVS last year, they were like, oh yeah, we definitely need to get this going. And I love the fact that we were able to bring together Canada and Egypt for this presentation. So I'm going to hand it over to the very capable hands of Andre and Hassan, and they will be giving you some more information on what they got done. So we'll see you all in a bit. Off to
Okay.
you.
Okay, so over to me. Thank you very much, Sanya. So, hello, LRVS 2024 America, Maintenance and Reliability Community, and everyone attending. My name is André-Michel Ferrari. Thanks again to LRVS for having me again this year. Wow, time flies. This is my third year presenting and fourth year attending LRVS. And so also a special thank you to my colleague Hassan Abdelnabby, who is the co-author of this study and co-presenter today. Hassan and I, as it was said before, met on LRVS 2023, and we decided to work together in order to share learnings to the community. Well, this exactly means, as Sanya said, that LRVS brings the community together. So it's not only a great learning forum, but a fantastic incubator of collaboration. So you'll see that today because we're going to talk about the PF curve. Hassan and I built one using real industry records. So it's not just theory, it's the real thing. So anyway, fasten your seatbelts and here we go. So this slide's about the authors and their pedigrees. You're welcome to go through it and know more about them. So in this study, Hassan wears the maintenance engineering hat, and I wear the reliability engineering hat. So moving on, today we'll talk about what the PF curve is about and how we gather records or data to build one. We will build it and then highlight the information it provides. We have enough records to build this PF curve, but we find, you'll see later on, that we can do other stuff with those records. Finally, Hassan will give us a practical overview of what this study can provide to the maintenance department. Moving on. In my past career, I've heard a lot about PF curves, mentioning here and there, but I never saw how one was constructed. Uh, I really like to know what's under the hood before I drive a car. So the PF curve is essentially a graph showing specific points corresponding to the health deterioration of a component over its lifetime. It represents the normal process of aging. Like for us humans, we age over time, our health deteriorates, and there are specific indications of deterioration that we can find over time. Have you ever heard a doctor saying, based on their diagnostic, this particular patient has 5 years left to live? This is essentially what a PF curve does based on a specific diagnosis criteria. For example, a vibration spike. And then we can estimate the life before a failure occurs. So in a PF curve, the P stands for potential failure. For example, the bearing is vibrating but still running, but it might fail in the future. F stands for complete failure. The bearing has failed and it cannot perform its intended function anymore. The interval between the P and the F uh, is the time we use to plan for mitigation or repairs. The PF curve is essentially built using condition-based monitoring records and failure records. The more resources we have, the more condition-based diagnostics we can perform. Therefore, the more P points we get, as shown on the bottom graph, the more PF intervals we will get. So in this study, for simplicity purposes, we will define only one point and one PF interval. I will now pass on to Hassan, and he will talk about the equipment we studied and the data points we used to get the PF curve. Over
Thanks,
to you.
Andre. Thanks, Andre. Hello, everyone. Before I start, I just want to say that I'm happy to be part of this amazing event once again. So we decided to work with our tissue mill. It's a huge and complex machine. It has three sections. Okay, the wire section, the F part, is responsible to form the tissue sheet paper, and the B section is responsible to transfer this sheet to the drying section in the Yankee section, and the last section is the Yankee section. This section is responsible for drying the sheet. In order to make the study as simple as possible, to help us show you how we can build the PF curve, we selected 11 rolls, which has identical bearings in type and size. In this study, we will focus only on the bearing defect. So next slide, please. In our study, we started the machine, the mill started in 2008. So we tried to gather a reliable and valid data. So we used our data from SAP system, which was implemented in our factory in 2015. We also used the maintenance log in order to get the F point, the failed port, and we used the vibration analysis program in order to come out with 7 vibration records that it is used to generate the B point. We only used 4 points because they are considered at or above our acceptable threshold. As for the vibration threshold, we are guided by ISO 10816, currently 20816, and we will talk a little bit more in the next slide. Next slide, please. So, vibration analysis of the bearing. So the bearing has 4 stages. For us, stage 1 and 2 are very difficult to see actual damage on the bearing. It's all about subsurface crack. We only consider these 2 stages in order to make sure that the bearing already available on our store, or we are on our progress in order to purchase the bearing. We are focused on stage 3. So stage 3, you can see an actual damage on the bearing, and also you need to remove it before it reaches stage 4, because stage 4, the behavior of the bearing itself can be unpredictable and it can fail anytime. Every stage has its own symptoms, and we follow all of that, and also we monitor the vibration amount, vibration level in order to make sure that it does not exceed the acceptable level of the ISO. So next slide. So vibration analysis of the bearing. So it is a complex process, but I want to make it as short as possible. We monitor the vibration parameters, so acceleration, velocity, or displacement, and see if there is any change in these values. So where industry know, in fact, is that if it increased 20%, you need to look at it in more depth and details. So if it increases, we look at the spectrum analysis and time wave analysis in order to make sure that we find the symptom of the bearing defect. All of that can help us to build up the baseline and set up the alarm level, which can help us reduce the amount of analysis. And also, if we are in doubt, we compare these values with another similar equipment. All of this are done in order to make sure that when we say the bearing need to be changed, we are giving the actual judgment. After all, condition monitoring, vibration analysis is a condition monitoring technique. So we monitor the condition all the time. So next slide. So this is an actual image for the software we have, but this is an shock pulse technique. So it is another technique that we use in order to give us a pre-warning even before vibration. As you can see, that we can detect the bearing failure, and also we can monitor the value of this change in amount of vibration. We use SPM in order to give us a pre-warning. Maybe a bearing has a long lead time, and we need to start working on it even more than the normal PF curve. So back to you, Andre, to start our reliability study.
Okay, thank you, Hassan. Thank you very much. Let's move on into the reliability study we conducted. So the PF curve will be built for the population of identical SKF bearings Hassan mentioned earlier. First of all, let's look at the reliability analysis process we use. So we get CBM and failure records and calculate the time to failure for each of them. The first graph on the left there. Because all the time variables are random, they are best represented by a statistical distribution in the graph in the middle. So we demonstrate that they follow a Weibull distribution. And once we have defined this distribution in the middle, we can do various calculations. I put an example here, such as probability of failure in this case. So this process will eventually provide us with the P and F points for the PF curve. So the assumptions are all listed below. Assumptions are important to ensure that the study is rigorous and well conducted. So moving on, using this process highlighted earlier, we have literally modeled how a typical SKF bearing in our sample is expected to deteriorate or fail over its lifetime. This slide represents the probability of achieving each point after a specific time interval. So we have two sets of data, P and F. So we have two models shown in this slide. So we have highlighted in the little box there on in each graph the Weibull distribution parameters eta and beta, which characterize the distributions for each category. So those parameters are crucial and unique to the model and will help us define the PF point. Moving on. So finally, here we are. We are ready to build a PF curve. So we use the scale parameter or eta value, which we obtained earlier. This parameter corresponds to the expected time to see a specific condition of failure. Therefore, the expected time to see the first P point, or the point where the high vibration threshold is reached, is around 57 months after the new bearing is installed. The expected time to see the failure point, the F point, is around 88 months after the bearing is installed. So the difference between those 2 points is, as shown on the graph, is 31 months or 2.6 years. And this value, 31 months or 2.6 years, is your PF interval. Moving on. So now let's see how we can interpret the results in a practical way. What does this mean for the person like Hassan who's going to operate and maintain the equipment? What we get from this study is a PF interval. We did not really focus on the vertical axis, which is the health of the equipment. We focus more on the horizontal part, which is essentially the elapsed time or lifetime. We now know that if we hit the P point, we have 31 months to do something about it before the bearing fails. So in other words, at the P point, the bearing is still functioning, but it is in a degraded state. Nothing has failed. However, we do not want to get to the F point where the machine fails, because if the machine fails, we lose production and revenue. And in extreme cases, it could be catastrophic with secondary damage. Or the failure could put worker safety at risk. Safety is a value and very important in industry. So therefore, we have 31 months to prevent a failure and plan a repair accordingly. Just on a side note, in our case, we have limited records, so the model precision is low. For example, for the P point, we use only 4 data points, which is very low. So our confidence boundaries are large. The model is not that precise. We still want to use the model as it's better than having no model at all. But maybe we want to be conservative or careful. In order to be conservative, we use the lower confidence bounds. It provides us with the lowest PF interval, which is 15 months or 1.3 years. This is half of the initial value, and that's why it's conservative. More data is always good, so we want to update our model as we get more data points. We will then have a better model with narrower confidence boundaries. We can also ask ourselves if we are satisfied with such a long PF interval. We can plan the change of a bearing maybe in a much shorter interval maybe. In this case, as shown on the bottom graph with the blue background, We can choose to implement another CVM test, such as lubrication, and define a shorter PF interval. So, for example, if we choose lubrication, we would have the same approach as vibration. This is find a threshold within our lubricant test results. For example, the appearance of a metallic contaminant that indicates impending degradation. So once we have defined this threshold, we would need to gather all the records and timestamps of those threshold occurrence after each bearing installed. The rest is exactly the same. It's exactly the same. The F point stays the same unless we have new data about failures and we can refine our model. So moving on, going a little bit, it's a busy slide. I'm sorry. Let's look a little bit further in the analysis. We did all this work. We have all those records. We crunched. We got only one value, which is the PF interval. Can we get more from the analysis? The answer is yes. But now we have to throw in another variable, which is cost. That is money spent doing maintenance or inspections. This slide shows the use of the optimization tool. I will briefly go through it. There are lots of details on the slide. I apologize for that. So if you need more information on how this is done, you're very welcome to contact me. So in the Egyptian context in Hassan's factory, if there was an unexpected bearing failure, it would bring down the mill at a cost of, on the left hand side here, at a cost of 13,000 US dollars, mainly in terms of revenue loss. If Hassan planned the replacement rather than going towards an unplanned replacement, if the planned replacement would cost him only 2,000 US dollars. Hassan does vibration inspection monthly at a cost of one US dollar per bearing per vibration check. So he does it monthly at a cost of $1. So this is low according to North American standard, but this is what it is. And then we move all this information into the optimization tool, and we find that it's cheaper to inspect the bearings every 2 months rather than every 1 month, as Hassan is currently doing. If he inspects every 2 months and he finds that the threshold has been met, he has 31 months or 15 months to be conservative to change the bearings. He also has a choice to do a planned replacement every 43 months. Sorry, on the right hand side here, with no inspection. But it is more expensive, sorry, to do a planned replacement than having an inspection strategy. Um, Finally, in terms of cost benefit, if Hassan inspects his bearings every 2 months rather than every 1 month using vibration analysis, his cost benefit is 31 US dollar cents, 0.31 US dollars per bearing per inspection. And when you add all the 22 bearings together over a year, it comes to 6.82 US dollars. It's a very low number, but this is what the model suggests. So if I take the same concept and look at this methodology again in the context of North America, where prices and costs tend to be higher than Egypt, using the same life statistics, we would have an increase. For example, we have an increase in unplanned failure costs from $30,000 to $25,000. We would have an increase in repair costs to $2,500. And the cost of doing one vibration inspection is significantly higher, from $1 to $50 per bearing. As before, it turned out that it's cheaper to inspect when we run it through the optimization tool. We find it's cheaper to inspect and replace the bearing if the vibration has been met, rather than doing a planned replacement. The suggested inspection interval is every 5 months, and so we inspect every 5 months, and if we hit the degradation threshold, we have the PF interval time to mitigate. So if we use the 5 monthly inspection strategy as suggested here, our yearly savings compared to doing monthly inspection goes up to it goes to we will be saving $792 per year. So Just to conclude here, our PF curve now comes a bit like a Christmas tree where we adding decorations to it based on the optimized calculations we did on the previous slides. We now add the recommended inspection schedules, by taking the same data we use to build a PF curve and adding some cost information to it, we are able to refine our maintenance strategy. So I've talked a lot now, but before I pass the microphone back to Hassan, I'd just like to make some concluding remarks on the reliability study. So as shown earlier, the PF curve provides good information, but it's limited to the PF interval. So it would be great to take the same records, all the records we used to do the PF curve, and add the cost information to it in order to get an improved maintenance strategy, as we showed earlier. Just a little teaser here with the information we have. We can even go further and build a reliability block diagram, but that's another presentation for the future. But it shows you how reliability engineering can be versatile, beneficial, and fun. We had lots of fun with Hassan. So having said that, over to you, Hassan, and thank you so much, Hassan, for working with me on this case study.
Thanks, Andre. So maintenance engineering review. So first of all, you need to monitor your performance. You need to keep record of failure times and mean time between failure, mean time to repair, machine availability. All of that, you need to analyze your performance in order to find the improvement point in your department. So we were able to build our case study because the availability of data. If we don't have data, we will not have nothing. We will have nothing, and we will not be able to build anything. So if you are not keeping record of your maintenance log now, start now. And if you want to find the correct KPIs that you need to monitor, you can ask your peers in the industry, because every industry has its own KPIs. Of course, you can come to the consultants and can help you to build your KPIs, but you need to monitor your performance. As for the BF curve, our conservative approach was 15 months. So 15 months for me as a maintenance engineer is important to have the time to plan the task. You need the time to determine the spare part needed and it's available or not. You need to locate the resources and the manpower needed to perform this task. So from my point of view, having a big or long BF interval is essential for you to have a correct behavior in your maintenance, because you want to perform all of that under the safety umbrella. So if you have more time, you will have better time to plan, and you have a good result at the end of the day. Which brings us to the last remark on this slide. So CPM or preventive. From my point of view, if you selected the optimal condition monitoring techniques that fit your failure type, you will save a lot of money and time more than looking at the preventive way. Because if you follow only the OEM general guidelines, you will end up by changing bearings or changing spare parts that does not need changing, depending on your situation. Following condition monitoring techniques like vibration, ultrasound, or any other condition monitoring techniques can help you save a lot of time and money. So next slide, please, Andre. So this is our final slide. So I just want to say, if you want to start, there is an easy way to start your journey in reliability. It can begin by creating your critical asset list, and then you can look for bad actors, equipment that cost you most pain in cost or downtime. If you integrate both of them, you will find the critical assets that needs your attention. You need to work on these assets in order to decrease your downtime of the whole plant, not only the critical assets itself. If you selected the optimum CPM tool for these assets and you find a suitable way to maintain it, you will end up by increasing the performance of your assets. So you need to analyze this performance, and you need to analyze your maintenance activity performance. But at the end of the day, you need to learn from your mistakes, you need to adjust it. And also, if you are working okay and you can see that your results are fulfilling your KPIs, you need to make it as a standard way to work with in the whole plant, not only the critical assets. So finally, I just want to thank Andre. It was a pleasure to work with you, my friend, and I hope we continue working together.
Yeah, so thank you, Hassan.
Thank you both, Hassan and Andre, for that awesome presentation on the PF curve. And I just want to make sure we've got some time for questions. And Andre, we've got Med, who's asking which condition-based monitoring tests do you prefer between, I guess, vibration and lubrication or others? And then what's the cost difference between them?
That's an excellent question. I guess it was for me, but then I was gonna pass it on to Hassan because I'm the reliability engineer. I just get information or data, and what I prefer might be relevant. I think it's more about how much it costs the maintenance engineer to maybe implement different types of condition-based monitoring. So, and the feasibility and the economics of doing it. But whatever works, I would usually liaise with the maintenance engineer, and whatever he can afford, whatever the company can afford, and also it's about whatever is most economical. Then we try and use it. But I'll pass on this is great question to Hassan. Which one do you prefer, Hassan?
Okay, every failure pattern has its optimum condition monitoring techniques. So if you want to monitor rotating equipment, I would say that vibration analysis can give you an early warning and cost-effective analysis, cost-effective solution to find the P point early as possible. Because in Egypt, lubrication analysis maybe costs 10 times more the normal vibration analysis. So from my point of view, it all depends on what the failure pattern you are seeking to understand. This, if you create your own failure mode and effect analysis, you will find out that using an integration of vibration and lubrication will give you an optimum results and confirm the results. Confirming the results is everything you need at the end of the day to say that this bearing is damaged and we need to remove it. No one to remove the bearing and find that there is still life going with the bearing and you made the wrong decision. So combining both of them can give you the best result. But from my point of view, for rotating equipment, vibration is the best way to understand if there is a bearing defect that it is related to the movement. But if you are seeking to know that if there is a contamination or something like that, if you select the optimum point to take your oil sample, you can get it's even warning, the pre-warning even before vibration, because it starts to wear out before to vibrate. So if you selected the optimum point, you will find out that at the end of the day, you know we are every time we are seeking that we need to know as early as possible the viewpoint. This is what I have in that.
Thanks, Hassan. And Vonda says, well said as well. And I think we're wrapping up on time, but wanted to share a few good comments out there. So Terry happily stumbled upon this on LinkedIn. So thanks, Terry, for joining us, and glad this was good. And I think we have one more quick question from Kaved here, who's do you accept 57 months as a normal mean time between failure for that bearing, especially when you take 22 different bearings into account? So quick answer on this one.
Sorry, what is the question? I beg your pardon.
Do you accept 57 months as a normal mean time between failure for that bearing, especially when you take 22 different bearings into account?
This is the expected life to get to the P point. It depends. It depends on the bearing. It depends on the condition that the bearing's working in. I mean, with Hassan, we said that this was acceptable. It made sense to him. This is an excellent question because So I always say I'm dumb. I'm just working with numbers that are given to me. But the way I validate those numbers, I go back to people like Hassan and say, hey, I got this number. Does it make sense to you? So he will say yay or nay. But in this case, the number that we got made sense to him within the environment he was working in. So then once it makes sense, if it didn't make sense, maybe we had issues with data. We didn't have enough data. There were data points missing. But in this case, it made sense. So
Okay, I want to comment on that before we end up. So, from my experience, so the bearing expected lifetime according to SKF is like 5 years with 60 months. But you need to make in your consideration the lubrication, the load, the temperature, and everything. That's why we said in our study that we took the conservative approach, even 15 months, because at the end of the day, mean time between failure is actually what is going to be done, but we are seeking out the B and F interval. We need it to be as long as possible in order to plan yourself. So 60 months or 75 months is acceptable in the industry for 5 years to have the bearing to be filled. But I have bearing here more than 5 years, and it was expected to fail after 5 years. If you create the good environment for the bearing, you will
and
make
that's
it
why
as
there's
long as
randomness in
possible.
the records. Oh,
You
just
need
going
the
back, it
bearing
just
to
came
last
back to me that
Hey
as
guys,
much as possible.
sorry.
I wanted to hear this, and I know everybody, but we're right on time. Thank you so much for sharing your knowledge. This was excellent, and you guys can when we take you off here, you can make comments. The people are asking more questions, and you can answer them in the chat. All right, thank you all very much.
Thank you.
Thank you so
Thank
much.
you.
Be ready
It was a
for our
pleasure.
next
Thank you.
session starting in 4 minutes.